Hello and welcome to the fifth in the series of videos aimed at developing retro games in vanilla JavaScript using the canvas element. My name is Anthony and please join me in my corner of the web where I like to build stuff in the browser with the latest technologies. Anyone picking up a new one-to-one fighting game for the first time will probably settle on their favourite fighter and then generally go straight into learning their special moves. And honestly, I say that knowing I've done exactly the same thing in the past, thinking that mastering the special moves will provide the best strategy for winning the game. Although taking a step back, any competitive gamer will likely tell you that attacking and defensive moves aside, it's usually best to understand their basic moves first, knowing where they have their advantages and disadvantages in speed, reach and height, amongst other things. In today's video, we'll be taking a similar approach. We'll be looking to extend our fighter's moveset beyond the current forward and backwards movements we've had for the past couple of videos. But rather than jumping straight into moving attacks, such as special moves, we'll focus on getting the basic moveset in first. This will allow our fighters to move around the available stage area at will. This common set of moves is available for all fighters, and will be the base for all other moves. These moves include the idle animation, jumping mechanics, crouching, as well as improving the forward and backward movement we currently have. To build this properly, I'll be introducing the concept of a state machine. We'll dig a little deeper into this pattern later in the video, but the general idea is that it will help us manage our fighter's state more cleanly. And to tie all this up, we'll then look to link the state machine to a simple form, so we can perform these moves with a click of a button. So before we get back into the code, I'd just like to mention that I've set up a playlist now for the video series, which if all goes well, you should now see a clickable link in the top right hand corner of this video. As previously mentioned, I intend to post a new video every 2 weeks now, along with a smaller and quicker video in between, more focused on general UI development. So if you like what I'm doing here, it would be much appreciated if you would like the video or even subscribe to let me know that you want to see more of my content. Okay, enough chatter, let's start today's video. Jumping straight in from where we finished in the previous video, we left Ken and Ryu moving back and forth across the screen, but unlike the videos before it, we now have them animating as you'd expect, with their forward and backwards movement. Unfortunately at the moment, this is all simulated based on the fighter's initial state, and the conditional logic for the size of the screen. This logic has been good enough until now to represent the movement and even the animations. But if we're going to implement a proper controllable fighter, which has the ability to perform any of their available moves, then we'll definitely need something more than what we have here. One of the last things we did in the previous video was to create two animations, using two keys named walk forwards and walk backwards. Just like our animation frames, we know we'll want more of these keys to extend the fighter's animation set, but more importantly for this video, their overall moveset. Although, rather than continuing to use named strings, the first thing we'll do is move these over to an enum object to keep the consistency across our files. So back in the fighter.js constant file, I'm going to create another exported const called fighter state. I'll next move our string values over and create new const names for them. I'm going to use walk forward and walk backward here. This enum object will be used to house all our fighters' moves moving forward. Now that we have this enum available, let's go ahead and replace any instance of the string value with the new enum value instead. First in our Ken and Ryu classes in the animations array, and then secondly in the fighter class for its move logic, remembering to import it and to correct any import paths if necessary. As the main goal of today's video is to extend the current logic to include the complete set of basic fighter moves, we will need to extend the logic in our update function to enable us to handle each move when required. Generally, each move we want to add would be defined as a specific action or behaviour that our fighter performs. This is also known as state. One of the most common traps that many beginner game developers fall into is not organising their state code in an efficient fashion. The most natural and probably default way you'd think to do this will be to have one large block of code that contains many conditional checks for every single behaviour the entity can perform. We've all been there, myself included. Your code usually ends up getting out of hand very quickly, becoming very hard to manage, especially as your code grows over time and your logic begins to collide. We've touched on state briefly towards the end of the last video, but to make managing our fighter state easier, I'm going to introduce a coding behaviour pattern called a state machine. A state machine can come in a few flavours, but typically is a concept for breaking down all the different behaviours an entity can perform and defining a state for each one. Your entity would start with an initial state and then transition to another state based on the action it took. An entity would usually have a valid list of transition states. For example, it would never openly transition to itself. This is to help us to guard against any incorrect transitions and therefore behaviours. As an example, we know a fighter should not be able to perform any crouching moves while they are in the air, or similarly, they shouldn't be able to perform any moves while they are dazed. So if we were to have code that would perform these checks in these invalid states, it would be inefficient, as we know these actions would never be possible. So, ideally, each state would be designed to only accommodate that behaviour, and would subsequently only know about the states it transitions to. This allows us to break down our code by state, allowing for smaller and more manageable sections of code. If you compare this to one large block of conditional checks we mentioned earlier, you can guess this is much cleaner and hopefully more easier to manage. So, with this knowledge, the next step is to add a simple state machine to our fighter class. We'll first accommodate for our current forward and backward movements, before extending it out to any others. Let's add a new property called states. We'll use this object to house our state machine. One thing to remember, the object will need to mirror the properties from our fighter state enum we created earlier, so any state we add there will also need to be added as a property here too. We'll start by adding each of the states we currently have, which we know are the walk forward and walk backward states. Each state will have two properties to handle our transition. These include the init function for initializing the state when it's first transitioned to, and then an update function for actually executing the state. Some state machines also have a finalize or tear down function here, but at the very least for now, I don't think we'll need it. We may also want to extract this out to its own class in a later video, but we only have one entity that requires states at the moment, so this keeps us aligned to the standard developer KISS and Yagini principles. Okay, so the next thing we'll need to do is add 4 more functions to our class for our state machine's init and update properties, in both the movement states we currently have. We'll start with the walk forward state, and create handle walk forward init and handle walk forward state functions. We'll then copy these function references back to the state's object properties. We'll do exactly the same thing with the walk backwards functions too, creating stubs called handle walk backwards init and handle walk backwards state. Another thing to note here is that we'll need to bind this to the scope of these calls, as they have been encapsulated in the states object and are outside of the scope of the class. We could have used arrow functions here instead, but I prefer to keep my code consistent when defining functions. So if you prefer this method, please go ahead and amend it as necessary. Before moving forward, let's rename our state property to current state instead, so that it's a little more obvious from a glance compared to our new states property. Then we'll replace all occurrences with their new name. Now let's update the change state function we created in the last video, as we'll now be using this function whenever we transition from one state to the next. So it will now take a parameter for the state we're looking to transition to and name this new state. We'll then set the current state property to it. As we've now changed the state, we'll also set the frame back to 0 too, so that the new state's animation is at the beginning also. And finally, we'll make a call to the new state's init function, so that it can be initialized prior to being executed. For this state to be executed though, we'll also need to make a call to its update function within our main update function, passing on the time and context arguments just in case the state requires them. With our new state function stubs in place, let's start moving our current logic from the update function. We'll start by moving our velocity assignments over to the new init functions. And in regards to our current screen collision logic, we'll unfortunately no longer need it in its current form, as we'll be changing state on demand rather than automating it when we hit the side of the screen. In fact, we'll look to reuse this code a little differently. We'll add another function called update stage constraints. This will be used to constrain our fighters within the limits of the stage, similar to before. However, we won't be changing the state here. Instead, we'll reset the fighter's X position. So we'll move the logic over to this new function, and then call this new function again in our main update function, passing in the context. As we're using the width from our current frame of animation, you might think we'll need to move this over too. However, we'll just remove it from here, as again we'll be doing something a little different. For now, I'm just going to add a new const called width, and set it with a value of 32. I won't go into the why just yet, as we'll be going over this and expanding it further in the next video, when we talk about collisions more in depth. With this new const value, we'll just replace the current width with this instead. And finally, for this function, as mentioned, we'll replace the current state change assignment to constrain the fighter's X position to both sides of the screen. The last thing we'll do is set an initial state. In the constructor, I'm going to use the walk forward state for now. Checking the result of our changes in the browser now shows that Ken and Ryu are moving forward in their specific direction and then stop at the edges of the screen, which is exactly what we wanted. Although this will unfortunately only work for moving forward right now. Let's quickly make a few minor changes so that it caters for both forward and backwards movements. As we now have a state machine and a change state function, we should never need to set the current state property manually anymore. So let's remove this line from the constructor and add a call to the change state function in its place, and move it to the bottom of the constructor after the states have been assigned. While we're here, we'll remove the commented line in this function too, as it's no longer needed, and then finally we'll correct our velocity assignments. If you remember in the last video, we multiplied the value of 150 by the direction. We'll need to do the same in both of the init functions, multiplying the velocity values by the current direction property, while setting the initial value to 0 in the constructor. Another quick check in the browser and everything still looks good. Okay, let's quickly change the initial state to walk backwards instead. And again, it still looks good, as both Ken and Ryu are now constrained within the limits of the screen. This proves our state machine is working correctly, and we're in a good place to start adding new states for our fighters. However, the only snag is that we need to keep jumping back to the code to change between each one. It would be better if we had something to allow us to test them individually within the browser. As front-end developers, the simplest answer is that we create a form, as that would work great for us here. So let's take a slight detour and add that next. Jumping back into the index.html file that we've somewhat abandoned recently, we'll go ahead and add a form above our canvas, and we'll wrap the canvas in a main tag. I won't go into great detail on how forms work here, as it's out of scope of this video series, although the form will consist of a couple of checkboxes so that we can choose between the fighters we want to interact with, a select drop-down to list the available states, and finally we'll have a button that will actually activate the state transition. We'll also add some minor CSS changes to accommodate our new form and elements. Again, I won't go into much detail here on the changes themselves, but we're ultimately setting up a few layout, colour and sizing changes so that the form appears above the canvas, and that the canvas itself sizes correctly. Just to ensure we've not messed anything up, let's have another check in the browser. You can see that we have a very simple set of controls above our canvas. The general idea here is that we can select a fighter from our checkboxes, use the drop down to select a move, and then press the button to ask the fighter to transition to the selected state. However, our drop down at the moment contains none of the available states. Let's look to quickly fix that and get the button working. Back in the index.js file, we'll create a new function called populate move dropdown, which will get all the keys from our fighter state enum object and add them as options to the dropdown in our form. We'll then ensure this is called when the page has been loaded within our event listener. In the browser, we can now see the dropdown has both the walk forward and walk backward states. The good thing here is when we add any new states to our fighter state enum, they will automatically appear here from now on. Okay, let's next allow the button to change our fighter state based on the selected option in the dropdown. In the index.js file again, we'll first need to get a reference to our fighters. So we'll create a new array called fighters, strangely enough, and move our Ken and Ryu object creation points from the entities array over to this one. Then in its place we'll just spread the fighters array back in. We need this reference as we'll be calling the change state function from our form button submit handler, which we will create next. So below our previous function, we'll create a new function called handle form submit, which will handle this event. Here we'll query the form and get the selected checkboxes first. Notice I'm mapping the return results so that I filter out just the checked values. If you look closely at the input elements attributes we created in our form earlier, you may have noticed the values attached to them were our fighter specific names, Ken and Ryu. We'll use these name values to check if they exist in our new fighters array. If they do match, we'll call its respective change state function and pass in the value from the select dropdown, which we know has to be one of the values from our fighter state enum object. So next we'll pass in our new fighters array reference into the function and then get the selected state option from the select dropdown. We'll then iterate over the fighters array and then check if any of the selected checkbox values match our fighter's name, and if so, pass on the state option onto the fighter's change state function. To call this function, we'll attach an event listener to the submit event and forward the event and fighters array. And with that, we should be good to test the results in the browser. Great, we can now control Ken and Ryu, or both of them, using the form. We are able to select either the forward or backward state from the drop down and get the fighters to dance to our will, pressing the button. With this now in place, let's go ahead and add some more states for our fighters. We've been missing the idle state for a while now, so let's go ahead and add that first. We'll first need to add the idle key to our fighter state enum. I'm adding it to the top of the list, as this is generally the initial state for our fighters. Then, back in the fighter class, we'll set up the states property with the necessary init and update properties, again with their stubbed functions handle idle init and handle idle update. If the fighter is idle, this usually means they are not moving. So inside the init function, we'll set the velocity property to 0. For now, that's all the changes we need in the fighter class. So let's go into both the Ken and Ryu classes and add the idle animation frames. Starting with Ken's class, I'll again copy over the frame data I prepared earlier. As before, this includes the source data for the sprite sheet and its origin point. Once we have the frames in place, we now need to set up the animation for it. Let's add the new idle key to the animations property and set up the animation frames as we did previously. Notice how we only have 4 frames for the idle state, but the actual animation sequence has 6 frames in total. This is exactly where the flexibility comes into play that I mentioned in the previous video. Just like the movement states, however, the idle state animation loops continuously. We'll copy the animation sequence and the key and paste it into Ryu's class, as again it's exactly the same as Ken's. I'll then copy the frame data for Ryu's idle stance from my prepared stash. Now that we have the idle state set up, it makes sense to set this as the default state. So back in the fighter class, we'll update the constructor and replace the current backward state with the idle one. And with that, let's have another check in the browser. Nice! Our fighters now start in their idle state for the first time. And just like before, we can seamlessly swap between the states from the drop-down. Adding that state was pretty painless, to be fair, so let's add something a little bit more complex, like the jump up state. Just like the idle state, we'll first add a new key to the fighter state enum object, and then create a new property for it in the state machine. Again, adding the stub functions for the init and update functions. We'll also add unique jump up animation frames to both our Ken and Ryu classes, along with adding the state key to the animations property. However, for the time being, I'm only going to use 1 frame. I'll come back to this shortly, as we'll first need to change our fighter class to accommodate the concept of gravity. Until now, we've only used the velocity property for changing the X position, although if we want to make our fighters perform a jump, we'll need to alter their Y position. So let's go into our constructor and alter the velocity property to now be an object that holds both the X and Y properties, similar to the class's position property. We'll set the default values for both to 0, and then update any velocity references in the class to use the new X property instead. While in the update function, we'll add a new line to alter the Y position every frame based on its Y velocity, similar to the X position we have on the line above. With this new line, our fighter can now move in any direction on the canvas based on its velocity values. To apply movements for a jump mechanic to our fighters, we'll also need to add a couple more new properties to the class. Back in the constructor, we'll add a gravity property and again set the default value to 0. We'll also add a new empty object called initial velocity. Just before I explain what these new properties are, we'll first override both of these new properties within our Ken and Ryu classes. Starting with the Ken class, we'll set the initial velocity object and add a new jump property with a value of -420. Again, not forgetting to copy the same structure over to the Ryu class. This is the initial value, or rather force, we'll apply to the fighter's Y velocity when the jump state is initiated, causing our fighters to project upwards. So back in the fighter class, we'll now apply this initial velocity value to our velocity Y value in the jump up init function. As we're only using 1 frame of animation, let's finally alter the animation logic to cater for this. We'll create a new function called update animation and move our current logic over to it, then add a call to this function within our update function. We'll update the logic so that it checks for the length of the current state sequence array, instead of the hard-coded value of 5, so that it works with any animation length. With everything in place, let's see the result in the browser. We'll select both fighters and choose the new jump up option from the drop-down. So the fighters are now jumping as expected, but we currently have no force pulling them down back to the floor, so they just keep moving further up the screen at the same velocity. In the real world, this is known as gravity, which funnily enough, we have a property just for that. So back in our fighter class, in our update jump up function, we'll look to apply gravity to the Y velocity each frame. However, it's currently set to 0, so in both the Ken and Ryu classes, we'll override the value there. I found a value of 1000 works well for gravity, so we'll use that, at least for the time being. Performing the same state change in the browser, and you'll notice we now have another problem. The fighters are being pulled back down to the floor as expected, but we have no collision logic to stop them going through the floor. Okay, let's look to fix that next. In the fighter class, we'll add a small conditional check in the jump up update function. As we know we have a stage floor constant available, we'll use that here. So if the Y position goes higher than this value, we can automatically switch our state back to the idle state. To complete this fix, we'll also reset the Y velocity in the idle init function. Another quick check in the browser, and perfect. We can now perform as many jumps as we like, as both fighters now reset back to the idle state when they hit the floor. So the next thing to address is the jump animation. At the moment we're only using one frame, but we know there are more frames we need to apply here. However, this animation works slightly different to the previous animations, as it does not loop, and furthermore the delay between each frame is different. So to implement this animation, we'll need to change how we currently perform our frame delay. If we take a look in the Ken class, and specifically at the animation sequences themselves, we need to be more flexible with our animations. What we really want is to have a unique delay for each frame. This would mean we could get really fancy with our animations, which honestly will help us for some of the later animations and states we'll be implementing. Okay, just like the frames array, I'm going to make each entry in the animations array an array itself. It will have two arguments. The first will be the frame key, as it is now, but the second will be a delay value in milliseconds. As before, rather than typing the code out again, I'll copy my prepared values over to both the Ken and Ryu classes, replacing all the animations we currently have. With this change, you can now see that all the animations follow this new format. Notice how the jump up animation has a negative value for the last frame. We'll come back to that in a second. As a side note, it may have some of the frame delays wrong here, but they'll do for now. By all means, let me know if you have a closer match to the arcade, and I'll happily implement them here too. So with both the Ryu classes now having a new animation format, we'll need to update the update animation function to work with this new format too. We'll first get the animation itself from the animations array. Then we'll deconstruct the frame delay from the second parameter of the new frame format using the current animation frame. With this delay value, we can now finally replace the hard-coded value of 60 with this new variable. Next, we'll add a small conditional check around our animation frame increment to only increment the frame if the frame delay is higher than 0. This is where our negative frame delay comes into play. If the last frame has a negative value, we're basically saying we don't want the animation to loop, which is perfect for the jump animations. Lastly, we now need to update our draw function to also accommodate this new format. We'll specifically disrupt the frame key from the current animation frame and pass that into the map's get function instead. And with that change, let's have yet another look in the browser. Great! Ryu and Ken are now animating correctly without looping for their jump up animation. Okay, I think the next logical state to add is the forward and backwards jumps. As we've done previously, we'll first add the new states into our fighter state enum in the fighter constants file, naming them jump forward and jump backward. Then we'll add the same state properties to our state machine. This time around, we'll leave the function references undefined for now, as we'll be doing some refactoring for these states. We will, however, retrieve the frame and animation data for these states and paste them into the Ken and Ryu classes before continuing. Notice how the new jump animations have a range of frame delays that now follow the new animation format. Okay, back in the fighter class, we're going to tackle the forward and backward jump states a little differently too. In fact, we'll also look to refactor our walk states from earlier, but more on that later. Instead of creating init and update functions for these new states, I'm going to rename the current jump up functions and drop the up part of that name, resulting in jump init and jump state functions instead. These functions will now be used for all our jump functions. We'll update the state machine to reflect these name changes too. This means regardless of the jump state you choose, you'll have the same jump initial velocity and land state. The only difference is that they'll have different animations at the moment. Although, for the forward and backwards jumps, what we really want is to have different x velocities too. This is where we bring the walk states into the mix. As we now have an initial velocity object property for our fighters, and we need to accommodate the x velocities for our jumps, it makes sense to expand this object for those states too. And yes, it makes sense to bring in the walk states also. Back in the Ken and Ryu classes, I'm going to add an x property to house all our initial x velocities for each of the states that require it. so at the moment, these are both the forward and backwards walk and jump states. Again, the values I'm using here are just guesstimates, and should be fine for now. We'll look to refine these later in the video series, to ensure they are closer to the original game. In fact, you've probably seen a lot of repetition in the Ken and Ryu classes. This is because Ken and Ryu are pretty much the same fighter in the original Street Fighter games. This actually makes developing the tutorial a little easier for me. So subconsciously, this is exactly why I chose Ken and Ryu. Although there's absolutely no reason we couldn't use a different character here, because as previously mentioned, they all should follow the exact same structure, but with different initial and state values. Depending on how long this series goes on for, we might go ahead and actually do that in a later video. We'll jump over to the fighter class now, and make our walk states use the initial velocity object too. But first, just like the jump states, we'll need to consolidate the forward and backward state functions into one set of functions, renaming them handle move init and handle move state. We can now assign the x initial velocity value to the actual x velocity property for the fighter based on its current state. We'll also add a nullish coalescing operator here to catch any undefined states and default the velocity to 0. To ensure the forward and backwards jumps get the correct x velocity now, we'll also call the new handle move init function from within the handle jump init function, not forgetting to update the function references in the state machine. Now that we've removed the direction from the walk init functions, we'll move it to the update function as part of the x position movement, and honestly, it makes more sense for it to be there. Okay, with that final change, let's see if we've broken anything. And by the looks of things, we haven't. Both Ken and Ryu have their forward and backward jump states, and their walking states unharmed. We can now freely change between any of the states as necessary. Before we move on to adding our last few states for this video, you may have noticed we're able to perform transitions from states that might not be possible at the moment. For example, Ken and Ryu can double or even triple jump. This might be great for a new feature, but unfortunately it's not part of the original game. You may remember I mentioned earlier in the video that we should ideally look to put a guard against this, if nothing more to protect ourselves from incorrect behaviours and potential bugs. We'll look to add a new property to our state machine for each of our states, and call this valid from. This will be an array and a list of any valid states from which the state can be transitioned from. We'll use this array as a lookup, and if we try to transition from a state which is not included, the request will be ignored. Working through the states in the state machine, I'll add a list of valid from states for each one. Notice how the idle state has quite a few valid states it can transition from. Next, to enable this feature, we'll update the change state function to use this new property. It will check against this array and short circuit if the new state is not part of this valid list. We'll also add another check to ensure the new state is not the same as the current state, and also short circuit if that happens, as it makes no sense to transition to the same state it's currently in. We'll again check this in the browser, and with this change, neither Ken or Ryu is able to perform more than one jump at a time. Somewhat disappointing, I know, but it does follow the correct move behaviours of the original game, which is what we're ultimately aiming for. So for the last part of today's video, we'll add the last of our basic moves, which is the crouching states, which strangely has 3 separate states and animations. The actual crouch itself, along with the crouch down and the crouch up state, as the fighters transition into and out of that state. As per usual, we'll start in the Ken and Ryu classes and copy over the frame and animation data for these moves. Then in the fighter cons file, we'll add the new crouching states matching the data properties we've just copied over. One thing to note is that I'm using a -2 for the last frame here. This does nothing but stop the animation from looping like before, but I'm using it as an indicator for me, to show that this animation is just a transition, and will look to move to a new state once this animation has completed. Next, inside the state machine in our fighter class, I'm only going to add the stub update function for the crouch up and crouch down states, as we won't be needing the rest. Instead, I'm going to add an empty function for those properties. This keeps our code clean while stopping any undefined errors. I'll do the same for the stubs we created for the other states too, just as a general cleanup. Finally, we'll update the necessary valid from states, starting with the crouch states and then the idle state. As we know, a crouch can only be transitioned from the idle state using the crouch down state, and vice versa. You can only get to the idle state from the crouch up state. While we're here, we'll also correct the typo for the idle state function name and remove the walk from it. Oops. Okay, let's look to add the logic for the crouch state in our new crouch down and crouch up state functions. As these states are simply animation states, in that their sole purpose is to transition from and to the idle state, we only need to check if the current frame delay equals -2, which we know is the last frame of these animations. We'll simply add this conditional check in each of these state functions, and change the state to crouch in the crouch down state and to idle in the crouch up state. And with that, we should now be able to transition into and out of the crouch state, which, checking the browser, it seems we can. So all is well. Right, I think that's all the basic moves and states implemented. And to be fair, I think that's where we'll leave it. But just before we finish today's video, let's do another little refactor, this time on the index file, as I'd like to move some of that code over to a class. In the Explorer window, we'll create a new JavaScript file called Street Fighter Game in the source folder, alongside the index file. From within the index file, we'll copy all of the imports over first. Then we'll move all the code from the load event listener, minus the populate move drop-down call. We'll also move the handle form submit function too. Then we'll wrap all the code within the Street Fighter Game file with a new class declaration. Next, we'll add its constructor and move the fighters, the entities and the frame time variables over to it. As this is now a class, we'll need to remove the const keyword and append the this keyword instead. We'll now start to abstract some of our code over to their own functions to make the code a little cleaner and easier to read, starting with the context code. We'll add a new function called getContext and move the necessary code over to it. We'll then add a new constructor property called context and assign it to this new function. In this function, we'll return the context variable to our local property. Next, we'll extract the update and draw for loops to their own update and draw functions, and then call these new functions within the frame function, which will now remove the function keyword from its declaration as it's no longer required. We'll also do the same with the handle submit form function too. Then we'll wrap the last two lines, the event listener and the request animation frame calls, within a new start function. Then we'll remove any unused references in the import section. Back in the index file, we'll start by doing the same and removing any unused references in the import section, and then add a reference to the new class. We'll then create a new instance of the class in the load event listener, and call the new start function from it. Before we finish, jumping back to the Street Fighter Game class, we'll look to fix any references we've broken. This consists of mostly prefixing the this keyword to all our local class properties, fighters, entities, frame time and context. So we'll scan through these references and update them as necessary. For our frame function, we will need to bind this to ensure the class context is passed into the main frame loop. We'll do this on both our request animation frame instances. For the handle form submit function, we can now remove the fighter's parameter and use the local property instead. We'll remove the this prefix from the document reference, but again, we'll need to bind this to the submit event handler to ensure it captures the class's context. And with one last check in the browser, all seems to be working as it should. Good stuff. Okay, I think that's where we'll leave it for today, as we're in a perfect place to extend the state machine to include moves outside of the basic moveset. Let's quickly review what we've learnt in today's video. This video has been quite a heavy code session, so please let me know how that has worked from a content point of view. As we now have a state machine for our fighters, this pretty much cements the initial gameplay mechanics. Just like the last video, I honestly thought this was going to be a shorter one, but it actually turned out to be my longest video yet in the series. So with that in mind, I'm not going to curse myself and say anything about the next video's length. That said, it will mostly focus on the control schemes and attaching our new state machine to both the keyboard and gamepads. We'll also look to start adding collision detection to our fighters, giving us a great platform to build upon and extend our fighters' states by incorporating attacking and defensive moves, although we'll probably look to implement a camera system to enable us to work with a proper parallel scrolling stage background before then. We may even play around with music and sound effects somewhere in between. So yeah, there's still plenty to get on with. As mentioned earlier, the schedule for this series will now be to drop a video every 2 weeks. The first week allows me to progress the code, while the second allows me to compile the content for the videos you'll see in now. I may start opening up the channel to more non-Street Fighter focused content, time permitting, as I would like to possibly discuss front-end frameworks and CSS specifically, which is what I do as part of my day job. And finally, again, I would just like to thank everyone for the recent likes, subscribes and comments in regards to my recent videos. Especially to Shagraf, who has reached out to other sources to announce my pursuit in bringing Street Fighter to the browser. And if nothing more, hopefully I'm doing something right here and you find this content somewhat useful. So with that, I'll say my goodbyes and hopefully I'll see you in the next one. And out.